Good evening, everyone, and a very happy Independence Day to all. So again, I am traveling now. I am not in India, so that's why I am sharing the pre-recorded version to you. But next lecture onward, I will be there, and we will do the live session. And if you have any questions regarding this or any previous session, we can take care of all your doubts in there. And during this live meeting, also, if you have any question, you can put the question on the chat box. My colleague team member can be able to help you out with that query. He can, otherwise we will take the questions in our next session. And you just go through this live recording of in the live meeting. And then today we'll discuss about the size reduction and the different examples numericals will there, which can help you to solve out the week 3 assignments. And if you have anything, you can directly ping me out. At the end, I will share my mail ID. You can drop me an email on that mail ID. Okay, now I am sharing my screen. Okay, so I think everyone can able to see my screen. So this is the today's lecture. And okay, so this lecture is all about the size reduction. This is the whole third week is discuss about the different methods for size reduction and how can we classify into 3 different large areas, or per se 4 large areas: crushers, grinders, and then ultrafine grinders, as well as cutting machine. And how we can use the different methodology, different principles, force which is being used for this particular methods, which are the different kind of equipment, how they can work. I am not much going into the equipments, so you can see. And I am just focusing on the methods, their explanation, and that examples based on those methods. So again, please watch all the lectures from professor, and it will be very helpful for you to understand each and every minute detail which we can't able to cover in the 1 hour, but we are here for solving your queries. Okay, so in this third size reduction week, we'll start from the method for size reduction. Then professor also explained different crusher, grinder equipments for the crushing purpose, grinding purpose, and for ultra fine grinding and cutting purpose. So these mostly these 3 session I will be not cover in these lectures, but all the methods will be covered, and based on the methods, different equipment based examples we will solve. Okay, so this is the outline of the today's talk. We will start for the what are the methods for size reduction, then the most important thing, which kind of forces involved in the size reduction. On the basis of that, we will do some energy power requirement calculation. Comminution is the word which we are using for the size reduction purpose, which is the scientific word. Then how to calculate the efficiency, what are the laws, and work index. These are the important things. Basis on this, there are various examples are there, which is very pretty easy when you are going to solve them, but pretty much easy. But you need to understand why these laws are there, which laws will be used for which place. Then examples, and for the we also see some preliminary guidance for selecting the size reduction equipment. And there are some examples on the basis of critical speed of protecting mills, which we are also going to understand today. So this is overall outline of the today's approximately 50 minutes to 1 hour discussion. And if you have anything at any time, you can go to the chat window and just ask your question over there, and you can send to my mail ID. But please attend the lectures and understand the things in a much detailed manner. Now we will start from the methods for size reduction. Okay, so that is a basic requirement for this talk. So we'll in the size reduction, why this size reduction things are required. So anyway, we understand about the particle size, shape, density, then the separating or screening of those particles in the earlier lectures. Now, whenever we deal with the solid particles, so most of the time, naturally, we are not finding the proper size of our on the basis of our application. Suppose you need some catalyst, want to form some catalyst, it requires a high surface area and finer size. Then in nature, maybe it won't be available in particular size. So that's why size reduction comes into the picture. Size reduction will be used to reduce the size of the particles, solid particles, according to the requirements in the industries or according to the applications on the industries. So which kind of application which is based. So that's why the size reduction is needed. Comminution is the generic word which is used for the size reduction. Okay, so generic term or scientific term you can understand. So wherever anyone can say the comminution, so you have to understand, okay, it is related to the size reduction thing. Now, smaller particles are desired product. Why most of the application or processes require the smaller particles of any solid material? Because they have the very large surface area. We are using activated charcoal in the various purposes in the packed bed and many applications. Why we are using the fine particle of the activated charcoal? Because they have the very large surface area. Now, energy efficiency of operation can be related to the new surface formed by the size reduction. Now, this size reduction operation, the dependency of the energy efficiency of the whole operation will be directly related to the new surface form. Okay, so whatever the bigger size particle which we reduce or which we reduce very much fine, so these new surfaces are forming now. So it increases the surface area, that can be directly related to the whole size reduction and energy efficiency of the whole size reduction operation. Now, common applications as the professor listed out. One is a crude ore crushed to the small and workable size. Always we need to use this size reduction for the crude ores. Then synthetic chemicals grounded into a powder in order to use them as a catalyst for different applications. Now plastic sheets are cut into tiny cubes. Sometimes whenever like some using some polymeric material and plastic material, then we want to use according to our application. Then cutting into sheets are also one example of this size reduction. Size reduction is always not crushing or grinding, it is also cutting into the shapes. Now commercial requirements to meet specific size and shape. Most important part of the size reduction operation is the commercial requirement to meet specific size and shape. So you always understand what specific size is your area interest, and according to that you need to understand which kind of operation you should go. Now reduce particle size, increase the reactivity of the solid. So many of the chemical reactions also use this size reduction operation. Okay. Now which are the different forces involved? Okay, so size reduction is always involving different kind of process like crushing. So in the crushing some compression are involved, so that kind of process are there. So you need to go to basic forces in order to understand the size reduction operation. So first and most important is the most basic one is I can say it's a compression. And the compression forces, you are just these are the some two materials and your solid is going to compress in between them, and the big particle will be converted into a small particle. This is the small example, but most of the coarse reduction of hard solid are using these compression techniques, and it is also known as a nutcrackers. So compression are using for the coarse reduction of the feed, hard solid feed. Coarse crushing implies reduction to size about 3 mm. Okay, so always it can be reduction to about 3 mm only. Then when we are going for this coarser size reduction, then we use this compression force, and it will be helpful for us. Another thing is impact, hammering. So some you can say the basic hammering force, like some hammer is there, your big particles are there, it is hammering continuously, and then you will get some small particle which is maybe which always be finer than the compression size reduction operation. So whenever you are going for the hammering force or impact force, the impact force will be provide very much higher size reduction than the compression. So this can be the first step, and from this can be the second step if you are going for the more finer size reduction. So it is also generally it's not the finer, but it is a medium size reduction. So it is known as a medium reduction operation. So it can be give fine, medium or coarse products. Now please keep in your mind that in compression also you will get the coarse, fine, medium product, but coarse product have very high fraction of your final product. But in this impact force involved, where fine, medium and coarse, medium amount of product has a very high fraction in your product. Now third will be the attrition or rubbing. This is the force when you apply which you are applying for getting a very finer size products. Okay, so attrition, rubbing, as you can see that attrition which will give much shear forces, maybe shear forces will be inward or shear stress will be inward in this kind of application. So the shear stress, shear force will be giving you a very fine particles from the soft and non-abrasive materials. So this is a force which you are applying for the getting very fine particles. That's why it is also known as a fine reduction. So side reduction in this applying this force can be occur with the help of attrition of one particle by one or more other particles. So particles itself is provide the attrition to the other particles, a rubbing force, or you can say in the scientific word shear forces and shear stresses. So at the end you will get the very fine material. Now cutting is a very easy according to the size and shape. If you want to cut the material, then you can cut easily. And cutting requires the cutting force. That's a very sharp object you are using for cutting the materials into the particular shape. So the basic example is vegetable dicing in many in the industrial scale. I am not talking about the households. So these are all the forces which are involved in. Now according to the force, example of equipments which is mentioned in this table. So if you talk about the compressive or compressive force, which have the principle of nutcracker, how it's work, that kind of principle, that kind of work application is there. For impact, hammering is there, attrition is the filing, cut is the scissors. So there whatever force is applied in the scissoring, these are all the basic physics. So you need to understand this as the physics laws only. And then examples are for the compressive nutcracker principle. Crushing rolls are the equipment which you are using. For impact, hammer mill are using. Attrition for a disc attrition mill and jet air mill. Many different milling equipments are used which are using this attrition force. And for cutting, rotary knife cutting. Now the most important thing which we need to understand, that in the size reduction operation, energy and power requirements are very huge in order to, if we compare it with the different other operations which are involving as a unit operation. So size reduction requires a high amount of energy. So that are the things we need to understand, because whenever we are doing the solving the example, or when we are designing some size reduction equipment operation in industry, so we always need to consider what amount of energy and power requires for this, because at the end economical calculation can be done with the help of this power requirements and energy requirements. So it is the major expense in whole this kind of size reduction, crushing and grinding operation, which is the power cost. During the size reduction, the particles of free material first distorted and strained. So it is there are various different processes also involved in the size reduction operation. The first, materials are distorted and it is also strained in order to reduce the size. Then the force will be applied, and for the stressed particle, you always have to consider the particles are stressed due to this distortion and straining operation. The particle converted into the stressed particles. Now due to this stress, if you are applying any kind of additional force, it will come into the convert into the fragments and due to reduce their ultimate strength or rupturing their self. That's why you need to understand that if you're providing direct additional force on any material, that will be require much more higher energy. So in order to achieve into lower energy, you need to first destroy them or strain them, and then on this trace particle, additional force is given, so it can convert it into the small particle. Then unit area of solid has a definite amount of surface energy. The creation of new surface requires work. Obviously, whenever we are creating the new surfaces, it requires some amount of work to be done on it, and then it is required the definite amount of surface energy to produce that work. And this work is supplied by the release of energy of stress and the particles are black. Whenever particles are black, there are much amount of energy will be released. Most time it will release in terms of the heat, and as it is correctly mentioned, that conservation of energy, whatever the energy release will be done in this particle breaking operation or ejection operation, it is known as it is converted into the heating. So you can see that whatever final material you are getting, it is has a higher heat energy than the fake material. So these are the importance of power requirements. Now efficiency. So size reduction is the one of the least energy efficient. Okay, so you can understand if anyone can ask any questions that which unit operation has the very least energy efficiency, and it is the size reduction, because major amount of energy will be reduced or will be only expense to given to the solid to come into the final form, and then only that force application will be done. So the studies most of the obviously energy will be dissipated as a heat, which is only heat loss. Less than 2% of energy applied to the solid is used to create new surface. So only 2% of the solid. Suppose you less than 2. Suppose you apply 100 kilowatt of energy, then only 1 to 1.5, 1.8 kilowatt only can convert the new surfaces into the solid material. Others are dissipated as a heat only. Now in operating size reduction machine, energy must also be supplied to overcome friction in the bearings and moving parts. Obviously, because the side reaction operation needs to do the hard job, then they need to convert the hard solids into the small part. So that part also that requires some amount of maintenance. So and because there are constant friction will be there in the bearing and moving parts. So this energy supply to generating that friction in all the moving parts of the equipment in order to reduce the size. The mechanical efficiency is the ratio of energy delivered to the solid to the total energy input to the machine. Obviously, we have whatever amount of energy which we are giving as an input into the machine, and what we are get at energy delivered to the solid, the exact solid which amount of energy is reach up to that. That is known as a mechanical efficiency, which we are calculating in order to calculating the effectiveness of our equipment or our person. The efficiency only ranges from 25 to 60%. Okay, so that is also most major times it is very less efficient processes. Now, this important part is that crushing laws and work index. So we will follow which kind of laws, and according based on those laws, what are the equations are there, and mostly these laws are not perfectly fit in each and every practical application, but we can use them to mimic our operation according to their principle. And what is the work index, work required in these laws, that also needs to be understood in order to solve the example, because in assignment problem maybe every assignment for this particular courses for particular discussion of size reaction, it's based on these laws only. So according to laws, many examples are there. We will also try to solve some examples here. Okay, so various laws are proposed predicting the power requirements and for the size reaction, and definitely they do not apply well in the practice, but these are the laws which we need to follow. in order to solve the examples. Approximate calculations are given. Actual efficiency of about 0.1 to 2%. This much amount of efficiency is there in the calculation. We always assumptions take the assumptions in this kind of laws that energy required to produce a small change d of dp. So dp, what is the dp? Dp is the diameter of the particle. If you want to provide the small change into that particle, suppose this is the diameter, sorry, this is the diameter dp. If you want a small change in this dp or this ddp, convert it into this. So this ddp is being calculated to energy being calculated to convert this produce this small change ddp in the size of unit mass of material is a power function of the size of the material dp. Now that can be represented by dp. This is the power. So change in power divided by change in the particle size. So my instantaneous change in power divided by instantaneous change in particle size is directly proportional to 1 upon particle size raised to n, in diameter raised to n. So dd by ddp proportional to 1 upon dp raised to n. This is the generic, okay, you can say this is the generic power law for size reduction. Power law. So for size reduction, okay, so all the laws are based on this value of n. We will change the value of n according to our law, and then we will get different laws and different equations, which are very easy in terms. If you talk about this, if you compare it this with other examples you already saw in screening and all, so these examples are very much easy. There are directly equations are given. You need to take the value from your example and you need to put the values and solve it. That's it. Now what is the Rittinger's law? Rittinger's law has n equal to 2. Okay, so when we are putting the n equal to 2 in this particular rate power law, dp by ddp proportional 1 upon dp raised to n, then we will get the Rittinger's law. So this law implies that the same energy required to produce a material from 100 mm to 50 mm as it is needed to reduce the same material from 50 mm to 33.3 mm. So according to this law, whenever because it is in the fractional fraction manner, when we are providing to n equal to 2 and solve this equation, so it is said that the same whatever the amount of energy is required to produce the material from 100 mm to 50 mm size, it is and the same amount of energy is required to 50 mm to 33.3 mm. So this is not the actual case in ideas in a practical scenario. This is not the case, but we need to follow this only if you are following the Rittinger's law. So as you can put the value of APS10, you will get this equation: P by m dot is the mass flow rate of the material, is equal to Kr. This is the Rittinger's law constant. This is not unitless constant. It has some unit. You need always need to focus that these are not a unitless constants in there in this kind of laws. Is it into 1 upon dpb, the product diameter of minus 1 upon dpa, so feet particle diameter. So that is also average feet particle diameter and average product diameter, obviously, because not all particles are same, and we are using this law in order to get the large means, or you can say the fine grinding, where a large increase in surface results. So whenever doing the operation which requires a fine grinding, this law can hold better approximate value of power requirement. It's not the actual, but it is better than the other laws. So for the fine grinding, we are using this Rittinger's law. P by m dot is equal to Kr 1 upon dpb minus 1 upon dpa. Now another law is Kick's law, n is equal to 1. So mostly this law is used for the coarse grinding when you are going for this cross assembly. So here as we are providing one n equal to 1, then it is a logarithmic function. So in this, the same energy required to produce 100 mm to 50 mm, which is again you need to do the half, and the same energy required for the half again 50 by 25. So this is also not the case, but maybe when we are providing the coarse crushing, then it will be useful. Now the equation is you can directly solve out P by m dot equal to Kk. Here it is not a unitless ln dPa by dPb. So this is the feed particle diameter. Feed particle, average particle diameter, and this is the product. Okay. Now this is more accurate in terms of coarse or crushing. So when most of the energy is in the causing fracture along existing cracks. Now we will go for the third law, Bond's law. Here n is equal to 1.5 as considered. So it is much more realistic way of estimating power required for crushing and grinding of the material. Whenever we are using the crushing and grinding, at that time the Bond's law will give you the better estimation. So please don't consider this. So this law postulates that the work required to form particle of size dP form a very large fit, the square root of the surface to volume ratio of product. Okay. So as you can see that this always can use for the very large particle size to the particle size of dP we want to convert. On the base, this law was always based on the square root of surface to volume ratio of product. Now, as you can see how this law can be work. So P by m dot proportional to 1, as dP is in terms of surface to volume ratio, we need to provide on the root of Sp by Vp. Then if we provide the value of Sp from phi s, we have this ferricity value 6 Vp by Sp dP. Then we can use the value of Sp by Vp from here as dP upon Sp by Vp is 6 upon phi s into dP. Then P by m what is equal to Kb, which is the Bond's constant, divided by under root dP. So Kb is a constant, depends on the type of machine and on the material class. So this law is much more practical in the nature, and it is depends on the different varieties of materials as well as different types of operations on the various machines. Now in all of this, work index is also one matter, that what is the work required. So work index is defined as the gross energy requirement in kilowatt hour per ton of the feed needed to reduce a very large feed to such a size that 80% of the product passes to 100 micrometer screens. Okay, so whatever your product is there, if 80% of that product can be passed from the 100 micrometer screens from the very large feed of the product, if you can able to convert the final product, very large feed material can able to convert the final product which can pass 80% into the 100 micrometer screens, then amount of energy required per ton of the feed is known as a work index. It's not a very difficult thing. If you want to go to understand much more in detail, then Kb, Bond constant, can be related with this under root 100 into 10 to the power minus 3 P by m dot. So power and m dot is the mass flow rate, which is tons per hour, and is equal to 0.3162 Wi. Wi is the work index. Kb is equal to, you can directly remember Kb is equal to 0.3162 Wi. And according to this equation, you can solve the value. You can got the value of the work index for your problems. Now, if 80% of the feed passes a mass size of dPa, this is in suffix, and 80% of product passes a mass of dPb. So what is going to understanding your, if you provide the work index in terms of kb, and if we use the Bond's law, then p by m dot is equal to 0.316 to wi 1 upon under root of dpb. This is the product average diameter, particle diameter, minus 1 upon under root dpa, feed particle average diameter. wi includes the friction in the crusher. Power achieved by above equation is the gross power. wi is also includes the friction in provided in this crusher, and gross power is we use it for this equation. wi is available for many standard solid materials. Already you will get the value of work index for different materials, because obviously it is not the same to crush the cement and you to crush the coal or coke, or you to crush some metal parts. So every material, metal ores, every material crushing requires different kind of energy, different kind of nature. wi is depend, work index depends on the materials, and it is available in many of the literature that according to a material in the book, like Adam Smith and other books, according to a material which kind of wi you need to use. The Bond's law holds reasonably well for variety of material undergoing coarse, medium and fine size reaction. That's why Bond's law is very well applicable in order to provide the size reaction for coarse, medium and fine size particles. Now we are doing the examples only. Now example is material is plus in a black jaw crusher. So different equipment will be was already discussed in the another 3 lectures from the professor. You can go through it and check which kind of different crusher, different grinders are there for getting the size reaction operation. So in this example we are using black jaw crusher. In this it is a fixed and this is like movable. This is a movable part. So average size of particle is reduced from 80 mm to 20 mm with a consumption of energy 17 kilowatt per kilogram into second, kilogram per second. What would be the consumption of energy needed to crush the same material of average size 50 mm to an average size of 15 mm if Rittinger's law is applied? We are directly mentioned we need to use the Rittinger's law calculation, and we need to there is energy required is given for 80 mm to 20 mm size reaction. Now we have to find for 50 mm to 15 mm. We'll put in the equation, we'll put this P and then P by m dot. This is direct P by m dot. We will find the Rittinger's constant. We will use that constant for the next phase of calculation. So if Rittinger's law is applied, which is not this is not the same example which is solved from professor. I just changed some values in order to get you can understand the very different easily, that you can use the different value and you can directly get the answer very easily. So feed particle diameter is 80 mm, particle diameter is 20 mm. So this is the law, which is Rittinger's law. P by m dot is equal to Kr 1 upon dPd minus 1 upon dPa. If we are substitute the values, that P by m dot is given 17 and other values of the particles, and we will get the value of Rittinger constant is around 453.33 kilowatt per kilogram into mm. You always need to take care of these units in your, maybe in your not in the assignment but in the end exam. It is important. Unit of is important for this what you can say constants in every laws. You can't consider it a unit list. Now in the second case we already got the Kr value. In the second case the TPB and dPa is for 10 mm is dPb and 50 mm is dPa. We just substitute the value, we will get P by m dot. So P by m dot, which we are getting that 21.1556 kilojoule per kilogram, as well as even in the second hour will be also come. Okay. Sorry. So 17 kilowatt per kilogram second. That is why kilowatt per kilogram, kilowatt per second is equal to kilojoule per kilogram. Now, same problem we again solve with the help of Kick's law, we will check the difference. So here Kick's law is P by m dot K equal to Kk ln dPA by dPB. So we'll get the value of Kk from here, which is a 12.263, and we substitute the value into the 50 mm to 10 mm equation. For the second part of equation, we will get the energy is 19.736 kilojoule per kilogram. Why? And here you will get 21.16 kilojoule per kilogram. So you can see that the value of P by m dot is different for both the laws. Now we are following another example. In that, a crusher is fed with limestone having a particles of 8 cm median equivalent diameter and discharges a product consisting of particle of 1.5 cm median equivalent diameter. The equipment operates with a capacity of 1.5 into 10 to power 4 kilogram hour and consuming 7.46 power. Its power is given, capacity is given, m dot is also given, diameters are given. If the requirements of the process demand the final size of the product with 0.5 cm of median equivalent diameter, decreasing the capacity to 0.75 into 10 to power 4 kilogram per hour, determine the theoretical power. Now you can see that this is the main feed diameter dPA. If you go for this 1.5 dPB, then these are the power and power and this mass flow rate is given. If we will instead of 1.5 we go for the 0.5 centimeter, then capacity will be reduced. Okay, so this is the mass flow rate will be reduced. Then we need to determine the theoretical power consumption under these new conditions. The same equation, everything is given, we just need to go for the constant, then we need to substitute the constant for the second phase of equation. So here it is not given to use which kind of law. So the feed is very much coarse, you can say 8 cm is very large diameter, so that's why we are using the Kick's law. Now first case, we have diameter 8 cm to convert into the 1.5 centimeter. We will use the Kick's law, P by m dot equal to Kk ln dPA by dPB. We will get the value of Kk from here, kilo. According to our unit, we need to substitute the values, and then we will get kilowatt hour per kilogram, 0.0002 means. Now we need to use for the second 8 centimeter to 1.5 0.5 centimeter, and we substitute the value of Kk and constant. Then we have the value of the mass flow rate, which is also, capacity is also reduced almost half. You substitute the values, and at the end we will get the power requirement 6.176 kilowatt. Here with the reducing capacity, the power requirement is also reduced, although our diameter, our size reduction will be much higher than this. It is very much higher, 8 cm 1.5, 8 cm 0.5 cm. But as we reduce the capacity, the power requirement also reduce. If we use the same capacity, then the power requirement will be very much higher. You need to understand all these things in order to run the economical process. Now this is another example. 2 kilowatt has to be supplied to a machine crushing material at a rate of 0.3 kg per second from 12.5 millimeter cubes to a product having the following sizes: 80% 3.175 millimeter, 10% 2.5 millimeter, and again 10% 2.25 millimeter. The distribution is on the basis of mass. So from the all of total mass, 80%, 10% and 10%. What would be the power which would have to be supplied to this machine to crush 0.3 kg per second of same material from 7.5 mm to 2 mm? So this is, I think, already explained example from professor, but this is the nature of the example is little bit different, and we need to understand what is the requirement of our whole process. According to that we will solve. So that's why I added this example also, but in assignments only simpler examples are there. Now, so here for the first case, power is 2 kilowatt, mass rate is 0.3 kg per second, and our diameter is 12.5 mm, which is the feed diameter. A product having 80%, 10%, 10% different material. Now if we use 80% material to a particular size, then we can use this work index formula according to it. So here we can use this 80% material has this particular size 3.175 mm, so we can take it as our product diameter, product particle diameter. We can use the work in this formula in the Bond's law. Now m dot is equal to 0.3 kilogram per second. Now we need to convert it into ton per hour. So thus that's it, 1000 ton is equal to 1 ton is equal to 1000 kilograms. So we have to multiply with 10 to power minus 3, and second need to be converted into hours, 3600. We need to divide it with the 3600. Now dp should be in millimeter, but should be in kilowatt. So at the end we will put all the value of, according to, for this particular equation, this power should be in kilowatt and diameter should be in millimeter. You always need to keep in mind this thing. This is important thing. Now Bond's law will be used over here. We will substitute the values, and at the end we will get the work index value according to it. And from that work index, if you substitute into the second part, for in which you need to go for 7.5 mm to 2 mm, which is mentioned in your equation, at the end you will get this you will get from here, and what you will need to substitute over here, and at the end you will get the power requirement for this second operation. Now a crusher fed with 500 ton per hour of a solid material for being crushed from a fish size of 3.25 inches to a product out of which 80% product material having 0.25 inch average size. This is the feed diameter, this is the product diameter, 80% diameter is there. We can use the work index calculation, calculate the power requirement for this crushing operation in kilowatt. We need to consider in the kilowatt power. In the Bond's law with work index, always value of P is in kilowatt, and work index is given 37.89. We just need to use Bond's law and substitute the values. Feed is 200 ton per hour. Okay, so there is little bit change. So instead of 500, it is a 200 ton per hour. Okay, so 100 and okay, so this is the already solved example, so I don't want to change the values. This is a 42.66. Work index is a little bit different, and okay, it's not 37.89. Okay, so don't consider this work index. Work index we will take is 37.89, and feed will take the 200 ton per hour. So I want to change the little bit example, that's why I just change the value of this numerator values. Feed average size is this 82.55 mm, 3.25 inches, and product size is 0.25 inches, which is nothing but 6.35 mm. Now if we substitute the value, we have m dot 200 ton per hour, work index is 37.89, P is needs to be find out, power requirement dpb is given, dpa is given. We substitute the values, and then you will get 687.16 ton per hour as a power. Okay, this is the feed. So 687.16 ton per hour. It's not ton per hour, it is a 687.16. Okay, you should keep in your mind that it is a kilowatt. So this is a power, not mass flow rate. So that's why you need to not perform the calculation blindly like I did, because of, you can understand, because of recording in the traveling I did some small mistake here, but you always need to consider power is in kilowatt. So that's why it is important to understand the units, understand the values, and understand the equations from the question. Like 80% product as well, it is there, we need to use for the work index. 1 minute. Now this is all about the examples which is there in your assignments, and I think not more difficult than this, even the very easier than these examples are there. Now other than this, in this chapter you need to understand the size reduction equipment, how can we select. So for different kind of operation, different kind of application, we will, and different kind of our requirement, we will use different kind of size erection equipment: jaw crushers, gyratory crushers, roller mill, hammer mill, disc attrition mill. Disc attrition mills, and these are very you can get the minimum size it to very less. Fluid energy mill is the very fine material product you will get, but the feed is also not much cost. So these are the different kind of applications are there. You just go into it and understand. If some questions are there, it's there in the exam or somewhere that someone is asking to the like this kind of course, then medium, and I'm just giving you example. Fine, very fine. They will just give you the 4 or 5 different what you can say equipment, and then they will ask it according to size, reduction ability. Just uh, pick them into this form. Somewhere they will give another one, and they will just do the some combination and permutation of this material equipments. So you can able to solve the examples. That's it. Even in the gate examination, sometimes ask this kind of simple examples. Now there is one more concept in this chapter which will be used for the numerical purpose, which is the critical speed of rotating mills. So rotating mills are these kind of mills in which in that there are different kind of particles which we are using, which can rotate and which can impact on the our main product or main solid particle. It provide the impact and impact force, and at the end due to this rotation and the hard solid metal balls or different kind of rods giving the impact on our solid particle. This will be used for the size action purpose in the medium scale. So faster the mill rotates, further the balls are carried up inside the mill. So mostly in that how this equation can be derivation is done. It is, and we need to understand what is the critical speed and all. So that's why some little information is given. So faster the mill rotation, greater power consumption, greater capacity of mill. But if the speed is too much high, then what happens? So you can understand the speed is too much high, so it will like achieve its centrifugal force, and it will be not providing the sufficient operation which we want to apply for the size reduction. So balance between this both gravitation force like this, that it the ball can be go up and from falling it down with the help of gravitation force and centrifugal force. We need to do the balance. If once it will convert into the centrifugal force, then there will be no much size reaction happen. So critical speed only calculated when we equate these gravitational and centrifugal forces. So this is the equation, very easy equation, very easy derivation. You have to just compare both the forces, and the equation is NC, which is the critical speed, is equal to 1/2 under root of g, the acceleration constant of gravity, divided by capital R and small r. Capital R is the radius of the mill and small r is the radius of the grinding area. Now operating speed must be less than NC. What is the reason? Because more than NC, centrifugal force will be active. So, and we will solve a simple example. Find out the operating speed of the ball mill by using the following data. Diameter of ball mill is 450 mm. Diameter of the ball is 25 mm. Operating speed is 40% less than the critical speed. So you need to find the operating speed. Before that, we need to find the critical speed, because we have equation NC is equal to 1/2 pi under root g upon capital R minus small r, and from this critical speed we need to find the operating speed, which is 40% less. Now NC is equal to 1/2 pi under g minus r. We need to substitute the value of 9.81 as a gravitational acceleration constant. Diameter is 450, r is equal to 225, and convert into the meter. 1225 25 mm is equal to 0.0125 meter radius. So NC is equal to 1.08 into RPS, rotation per second, and 4.8 rotation per minute. Now we need to convert into the operating speed. then it is a 40% less, that's why we just divided by 1.4 and we will get the 46.29 rpm. It is the operating speed of this wall mill. Okay, so this is the example, and this kind of different example will be there in the your assignment problem, and you can go through the books and you can try to solve this kind of example. Only you need to always understand and remember the formulas. All other things are very simple. You just need to put the values in this formula, and at the end you will get the answers. So this is all about the size reduction operations and what kind of examples are coming from this kind of discussion. So that's why we started with the basic discussion of the what is size reduction, what are the forces using, what are the laws and work index and requirements are there, why it is important in order to size reduction, which equations we follow. According to them, we solve some examples, and another kind of example are coming for this ball mill operations, and this kind of example sometimes in coming in the gate examination also. So you always need to focus, or if you don't know the formula also, then you just need to do the equate the forces like gravitation and angular force, and you will easily get this equation. Now the books and reference are the same books of we are using for the McEwen Smith, Ortega Rivas and Richardson, Corson Richardson model, and you can go for many more are there. Examples are using from these three books. Now at the end I just want to quote the famous scientist C.V. Raman, engineer and Nobel laureate. I am the master of failure. If I never fail, how will I learn? So what is the meaning of this quote? That he is saying that if you are not ready to fail, then you are not ready, or you are not succeed in the future. So that's why you always need to do the accept the failures in your way and overcome those failures by converting them into the success. And this is my mail ID. Please note it down to this mail ID. Whatever doubts you have, whatever questions you have regarding these examples or regarding some theoretical portion, you can write to me, or you can write to currently in the chat boxes. So we will take care of your exam and take care of your questions, and from the next session onwards we will do the live session, and anything which you want to learn you can come. So I want to stop sharing now. So with this, thank you all the best for listening or watching my recorded videos, and mostly next time we will meet physically on a virtual mode. Until then, please take care of yourself. Again, very happy Independence Day to all. Thank you.